And you know, when it comes time to take the test, you're welcome to bring any note packets that I give you, any notes that you take on your own. The only thing that you can't bring is like a textbook or a printed up version of a textbook. I've had somebody do that before. It's like, oh, you said I could bring notes, and I was like, yeah, but what you did was you printed a PDF copy of a textbook and brought that. That's not notes. Like, so that's a different story.
Printed out versions of your own notes.
Printed out version of
Your own notes.
my own or your own?
Your own. Students.
Students' own notes. So like you hand wrote notes or you typed up notes. I don't see why not. As long, I mean, the only way I'd have to be sure that it's your own stuff. Now, you're we talked, but you know, like basically, if it says hardcore brace at the bottom of it, like I'm gonna be like, all right, this isn't your stuff, you know. So, and then if I see like little lines where that was cut off or you know whited out, that's not good stuff. But yeah, that can be a little dangerous, but you know, it's you know there are exceptions, I guess.
Are we able to collect any tests using that number?
Yeah, yeah, that's all fair game. Tests, well, we haven't done much with quizzes, but can't see how a printed up tech assignment would be overly helpful because it's all in GeoGebra language, but that would be fair game too if you could somehow like make use of that. Yeah, anything that we produced in class together. That's it. Uh, okay. Anyway, so null, column space, and dimension rank. So the null space, we already talked about this, is the, I should not say that because I'm going to end up saying that for everything. Written as null A is set of solutions of the homogeneous equation AX equals 0. All right, the null space of an n by n matrix A is the subspace of Rn. Also, the set of solutions to a system AX equals 0 of m homogeneous linear equations and unknowns is a subspace of Rn. All right, so all of that is really us just saying that if you find a null space, you're in fact finding a subspace, a type of subspace. Column space, set of linear combinations of the columns of a matrix, all right? And so that would be all of them, the whole shebang, all right? But then we start looking at the basis of the column space, which is something different, all right? Column space is a subspace of your Rn. Right? Column space of an m by n matrix A is all of Rm if and only if the equation Ax equals b has a solution for each b in Rm. Right, so that's telling us that you're going to have, so it's an m by n matrix. You'd have to have a solution in each row when you bring it down to a reduced row echelon form. So basically, it's saying that you don't have necessarily any free variables. Right? So definition of dimension: dimension of a vector space is the number of vectors in a basis for V. All right. So once you develop a basis, the number of vectors that make up that basis would be your dimension. All right. And that's I kind of alluded to that yesterday. I spoke about it kind of off the cuff a little bit, but it was basically saying that when you have vectors within your matrix, some of them take on the role of the basis of the column space, and some of them are just three variables, or they're not necessarily required in order to span whatever the vector space is. Right? So if that's the case, then why would we count them towards the dimension of the actual vector space? V is an n-dimensional vector space, and S is made up of the columns. S is linearly independent, then S is the basis for V. So if we can identify linear independence, then we have shown that S is the basis for V. All right. If S spans V, then S is the basis for V. All right. But basically, if you identify one, that's good enough because they go hand in hand. Like if you got one, you got the other. Okay. Dimensions of null and col A, so null space A and column space A. Dimensions of null is the number of free variables in the equation, and dimensions of column space is the number of pivot columns in A. So this is talking about when we're talking about the dimensions of the column space of A. We're talking about the number of vectors that make up the basis. All right. So I refer to that as the relevant set of vectors within the matrix. All right. That is defined as the dimension of the column space, which is also known as the rank, which we get to in a couple minutes. All right, so I believe I started this one yesterday. We wanted to determine if U belonged to the null space of A. So obviously it's a different page in your notes, but in this new one I have it slightly organized differently. Determine if U belongs to the null space of A would be if it gives a zero vector through vector multiplication, vector matrix multiplication. So what we want to know is AU equal to 0. Right? Because a null space, again, is the solution to the homogeneous equation. All right, so if I'm already giving you a solution to an equation, all I'd have to do is verify that it checks out to give you the zero vector. All right, so you can do it on a calculator, but I think the calculations here aren't that bad. We're looking for a 3x1. 2 minus 6 plus 4, that's going to give you a 0. Negative 3 minus 2 is negative 5 plus 5, also 0. Negative 5 plus 4 is negative 1 plus 1, also 0. So, yes, it does belong to the null space. All right. Pull out the old calculator here real quick. I'll put it in as a 3x4. I'll actually solve the matrix equation. 2, 6, 4, 0. You obviously don't need the 0 for homogeneous, but I will put it in anyway. All right, so I'm just solving the homogeneous equation ax equals 0. All right, so just to see what happens. Oops. Oopsie daisy. Also gonna do that. And then just pin this baby. Sounds weird. We'll just live with that as is, you know. Okay, so you look at this and you say, is there a way that I can tell from the reduced row echelon form that U is a solution, it belongs to the null space? Well, let us develop a solution here. X1 equals, that would be X3, right? X2 equals negative X3, where X3 equals X3. So I can let X1, 2, 3, be equal to X3 multiplied by 1, negative 1, 1. All right. Now, we could write this as a parametric form. You know, let X3 equal T, in which case we're looking at a scalar multiple of the vector 1, negative 1, 1, giving us the solutions, basically the null space for the solutions to the homogeneous equation. So anything that is a scalar multiple on 1, negative 1, 1 will do the job. So if I let X3 equal 1, I get U. So good to go. Now, if I did all this work, I mean, I can't come up with a matrix off the top of my head, obviously, where this would happen. But if I had, let's say, 1/3, negative 1/3, 1/3, I'd say, well, I didn't get U, but if my scalar is 3, then I would. You know, so you can manufacture the U just by a scalar multiple on your null space vector, the basis of your null space. All right. So, number 2. Now, I mean, all that being said, the obvious way of doing this would be to just multiply these and get the 0 vector. But you know, if you weren't given this vector, that would be the approach that you would take. All right. So this is the null space of A. All right. So in number 2, if the column space of A is a subspace of R to the K, what is K? All right. So basically, they're asking us for the dimension. You know, when I say R2, that's in 2 dimensions. R3 is in 3 dimensions. Real space, 2 ways, 3 ways, 5 ways. All right. So if I'm looking for the dimensions of the column space, I'm looking for the basis of the column space. Basically, looking for the number of pivot values that would make up the column space. All right. So not many situations that I can think of off the top of my head where you would need to use a calculator in this unit. Not need to use a calculator. That's horrible. That's the exact opposite of what I was trying to say. Where you'd need to do stuff by hand. Oh, jeez. First thing I said would give people a heart attack. Unless you interpreted it as the problems are so easy you don't even need a calculator. But that's not the case. There's a reason why it's open notes. Sorry, I forgot my throat. Honestly, the real reason why it's open notes more than anything else is not because the questions are overly difficult. It's because when a question asks you to find the basis of null space A, most people's first reaction is like, all right, wait a second, what the hell is that again? So that's really what it's coming down to. All right, so column space of A, again, we're looking for the dimensions. The dimensions would be the basis vectors that make up the column space. So I am looking at anything that's got a pivot, meh, meh, and one final meh, right, meh. All right, so K would be equal to 3. Right, which tells us that we're looking at a free variable mixed in here somewhere. Right. Now the null space, well, we just kind of did that, so that's not going to be difficult because we're looking for x. And again, we're kind of operating under the assumption that you understand the background work, and that is that we're saying that ax equals 0, that you have this matrix vector multiplication thing going on here where you're looking at I sometimes take too much for granted. X1, x2, x3, going right back to, I believe, unit 1. All right, so, 4, sorry. It's like there's the perfect amount of space for 3 x's to be written in there, but I just can't write. And then it would be a 4-unit vector for 0. 3 by 4, 4 by 1. No, it's still 3 by 1. Okay. Yeah, so that part is fine. Okay, yeah, so that's what we're looking at there, which then leads us to the augmented matrix, which leads us to the reduced row echelon form, which then leads us to the conclusion that x1 would be equal to -9 x3, x2 would be equal to 5x3, and then x4 would be equal to 0. All right, so tucked in there, because it's not represented because it's not a pivot, we have x3 equal to x3. Since x4 is actually a pivot value, yeah. it has a coefficient, so we do have an x4 here, and it is equal to, well, when you have the zeros on the outside, it is particularly equal to 0.
That's why you're able to have the pivot point in the last column in part A, because there's technically zeros on the outside.
Exactly. All right, so what we would say here, well, it's not actually necessary that you indicate the 0 vector, but I'll do it anyway. So my x solution would have, because x4, you could look at this one of 2 ways. You could look at x4 as being equal to 0x3. If that's the case, then you have a single parametric vector. If you want to look at it as a constant, then you would create a brand new vector for that, and then another parametric vector to address the x3s. 1, 0, sorry. But this guy's not necessary, because through just addition of vectors, it would go away anyway. But you can go other way.
I just have like 0, 0, 0, 1. I thought like x4 would be a free variable.
That would be if you had a column of zeros in the bottom. I'm sorry, column of zeros, a row of zeros in the bottom. Right, so close. Right, so this, or same thing without the 0 vector, it'll be fine either way. And it kind of makes sense because one solution of the matrix equation ax equals 0, it would make sense one solution would probably be the 0 vector. And in fact, anytime we write a parametric vector solution, we could in fact add the zero vector onto it. In the previous one, we could have done that too. You know, there's nothing wrong with adding a column of 0, 0, 0. It makes sense. All right, so dimensions of the null space and the column space. Oh, that's not my calculator. That's my calculator. Is it? Oh yeah, it's good to go. Look at that. That's awesome. No? Oh, it's terrible. Ugh. Well, we just need the pivots, right? Right. We do have the pivots. So we could already state the dimensions of the column space and the null space.
Yeah. No space needs to like a variable.
For times that there's zeros.
Right. So I'm actually just going to indicate what they are. So C1, 4, 5, 7 is going to be equal to 4. Oh, row space, not even there yet. All right, so every free variable leads to a solution, so that's kind of the point of the previous questions. So in the previous two questions, just to kind of justify these things, well, more so the second one, we had 4 columns. 3 of them ended up giving us the pivots related to the column space, which gave us the dimensions of the column space. The one left over led to a single free variable. That single free variable led us to a vector related to the null space, right? So if we're looking for the dimensions of the null space, we're looking for the number of free variables that would exist, right? So long story short, that just tells us that we're looking for columns that are not pivots within our original matrix, all right? So that would be C2, 3, and C5. So other dimensions of the null space would be